Welcome to our lecture, Solar Electric Energy Systems. We are now at the 5th lecture. Today we'll talk about PV system, the wiring, inverters and the different system configurations. Just a repetition from last lecture. It was rather extensive. So this is the effect of a shaded cell. This is a curve of a shaded cell, the black number 1 here. And this is a curve of a fully illuminated cell. And this is number 2 is the series connection of 35 fully illuminated cells. So you add up this, and theoretically, if number 1 would be fully illuminated, then all 36 cells would create that IV curve. So we say now cell number 1 is now shaded by 75%, for example, due to a leaf. Then it would create that curve if we just observe the positive part here in order to create a full IV curve of all 35 cells plus one cell connected in series. They are subject to the same current. So all the same current has to go through each of the cells. And to find a common current, this is a current here, the current value here, you just have to do a superposition of the current. So we take this current of the 35 cells with full illumination and this shaded cell. This we don't find on the positive axis here because the current is so low. So we have to take into consideration the negative part of that IV curve, and then we find a point here. And together we come to that point. If we continue that to each of the points, then we come to this red curve. And this represents the IV curve of a module consisting of 35 illuminated and one cell with a leaf on it that shadows by 75%. Here again, just here, not 36 cells, but 3 cells only to show that. So we have here 3 cells interconnected in series. So each is plus minus, plus minus, plus minus, and so on. And the voltage is 3 times the voltage of each cell. Now we have the shaded condition. That means the current here is drastically reduced. Here even more extended here. And if we think about what would be the effect of a drastically reduced current, we can even think about take current as 0 to consideration. So that would be equivalent to a virtual break in this solar cell. There is no current going through that solar cell anymore. And this would mean that here we have the load here still and the remaining 2 cells. And here the voltage at the upper cell is here plus minus. So we have minus here and plus here. And that's in opposite to the original voltage of that cell. Therefore, we have a negative voltage on that cell, as you saw already on the IV curves before. How we can overcome this? This is via a bypass diode. This is a diode that is without function under normal conditions. So this just if this cell is fully illuminated, there's plus minus. So plus minus at this bypass diode means it's in blocking condition. Those are no effect at all. And now if we have this reverse voltage minus plus, so with minus plus, it's in conducting condition and the current is deviated here around the shaded cell, and we have still a considerable current going through the whole system here. If the shading is not 100% but less, so there is a division between the rest current and the bypass current, and you add up all this current in your total current here. These bypass diodes are usually located in the terminal boxes here. It's quite difficult to install a bypass diode for each solar cell. So for cost reasons, we just bypass a string or even 2 strings, like in this case. So we have a solar module, solar matrix. So we have a string going to the lower part of the modules and then another string coming back. These arrive here and we just bypass with this bypass diode these 2 strings. Same for here. So the outer 2 strings and here the middle 2 strings are bypassed by this bypass diode. So this module consists of 6 strings and 3 bypass diodes. Here we see the effect of the bypass diode in terms of the number of bypass diodes. For example, if we have our module with 36 cells and we have only 2 bypass diodes, we have a curve like this. So half of the module is bypassed there, and therefore the half of the voltage, you find a drastically reduction. If we have what we saw now at the 3-cell module, if we have bypass diode at every single cell, and then you see that we just have a loss of the cell. Plus you have to consider, if you go back to the shaded cell, you have to consider there's a voltage loss also along this bypass diode. So we have the loss of the cell, so we lose 0.7 volts, and if it's a bypass diode, additional 0.7 volts. So worst case here, we lose 1.5 volts, and that's you see here in that picture. This is shaded by also 75%. So you see here, if we stay below, if we consider the currents which represent below 25% of the original current, there is no change at all to the original IV curve without shading. It's a bit hard to find the maximum power point, so it's quite easy at the module without shading. So you just have here the maximum power point. So the voltage times the current is maximum. That means you have the maximum electrical power output of here. But what happens if the module is shaded? We find 2 maxima usually. So you have a maxima here and a maxima here. This also confuses even the maximum power point trackers, or some of them. If you have a very simple one, he just increases voltage a little bit and finds out, oh, power is decreasing, so he go back to this and or go the other way around. So he just finds one maximum power point. But what would happen here if you have, for example, at a 75% of shading, maximum power point tracker would stay here. He won't find that point because he goes back or say, okay, power is reduced, I go back to that point. And so we would stay at that maximum power point, and you would have a drastically reduced power output. Only if you do a full swing along the full range of voltages, you will find that maximum power point. So this depends on the algorithm of the strategy of the maximum power point tracker, whether you just do a differential tracking here or whether it does a full tracking over the full voltage. Sure, it takes longer time to do that, because you have to carry out all the multiplication to find whether the power is increasing or decreasing. But at the end, you have the best results. Some of the strategies are hybrid, so they do usually just a differential maximum power point tracking. And after 1 or 5 minutes, they consider a full swing of all voltages and then find a global maximum of the maximum power point. You see, it's quite interesting here to see that at 25% of shading, you find still the maximum power point on the right part of the picture here, also for 50% of shading. So it's all very close to the original curve. And here you see the effect of the full shading here. This is a power curve now. So you have here the MPP at no shading. So here's the maximum power at about 27, 28 watts. If we have 25% shading, we have a reduction here to about 23 watts and so on. And if we go to 75% of shading, we have still here about 13 watts here, but at a very much different voltage level, as you see here. So this has to be considered if you consider follow-up components, for example, inverter or battery charges. So here you have still a lot of power, but the voltage is drastically reduced. And some of the subsequent components cannot digest that low voltage. So you have to consider a DC-DC conversion to lift that voltage up at reduced current to higher voltages in order to keep your system still under operation. This is a more modern approach for the bypass diodes because you want to avoid the losses. So this is an electronic device that detects shading and then carries out the bypass process without the losses of the bypass diodes. Unfortunately, this was too expensive, so it wasn't applied by the module manufacturers a lot. Cost was about, I think, 20 euros or something like this, while nowadays module costs only 100 to 150 euros. So this was quite a considerable cost. And if you compare it to a bypass diode, which costs maybe 50 or 40 cents, so this was unbearable. Interconnection of modules, so we already at the end of the module, we come to the connecting points. Formerly, the terminal boxes had screws where you can put in your cables and so on. But as the system voltage increased, especially while you have DC voltage, it might be quite dangerous and also quite time consuming to connect each cable with a screw in a terminal box. Nowadays, modules are equipped with such plugs. They are fail-safe plugs, so you cannot connect the other way around. So just here, for example, the positive pole, and then you have negative pole. So this is quite proof. And also you cannot touch the conductor here, because here you have a plastic tube around it and the conductor is inside here. Also is sealed against humidity here. And also you have a snap-in configuration. That means it's quite fast to install, but very hard to disinstall, because you have to press both noses here at the same time. This is usually only possible with a tool, but usually if you install a module, it stays there for 25 years and you don't have to consider deinstallation. The configurations, what you can do with the modules, you can put them in series or in parallel. What is usually carried out is, for large-scale installations, that you interconnect as much as possible modules in series up to the maximum permitted voltages, which is nowadays 1000 volts. This will be overcome by a voltage of 1500 volts or even 2000 volts is under discussion. Here the large-scale configuration with the so-called string diodes. While you may have voltage losses due to shading, for example, and there is a voltage loss here, then the voltage of one string can be lower than the other strings. There might be a possibility that here a current not goes to the inverter, especially if it's in open circuit conditions. There might be a current going in a string, for example, this string, for example, is shaded here. There might be currents going into that string, or even not one, several strings. If all the voltage is higher than that string, then the current will flow into that string and may destroy some of the module, or at least two hotspots. Therefore, you have usually string diodes. They act as a valve, so they let the current go in, but they block the incoming currents. Nowadays, because the string diodes, they are costly and they have to support the full current of the string, and you have some voltage losses along the string diodes. So nowadays they are substituted by fuses. So these fuses are cheaper and they have a much lower voltage loss along the fuse here. But still you find a lot of system configuration with this string diodes. If you go to a large scale system, this is a PV generator, and then you have here the load, which is usually inverter that feeds into the grid. There is some distance between those two components, between the actual power plant and the inverter, and you have some cable losses here due to the cable. And in exercise we calculate those cable losses and do also an optimization. Is it worth, for example, to buy a better cable with a larger diameter in order to reduce the losses but pay a bit more and so on? And we do in the exercise, we do such a calculation. Notes for the DC installation. So the problem is that the modules are live. That means there is already a voltage on it. So you cannot switch them off, because as soon as there is light, a photovoltaic is operating. Even if you try to shade it, there is still the voltage there, which might be quite dangerous. So they might work on the full nominal voltage. So you have to really have a really light-proof material to cover this. At least you reduce the currents. You might also reduce the voltage if you make it really light-proof. As I mentioned already, the level of the DC current is proportional to the irradiance. The nominal voltage, on the other hand, is reached as when you have low irradiance. PV arrays are current sources whose short-circuit current is only about 20% above the nominal current. That should be taken into consideration when designing protection technology, fuses and circuit breakers and so on. This is a bit different if you design a normal household circuits and so on. You design the short circuit current protection much higher, but here's only a difference between the nominal operation current and the short circuit current, which is a maximum current is only about 20%. Also important is that the current is DC. That means there could be a permanent arc. So therefore you should consider special fuses and switches which are designed for DC. So the contacts are a bit farther away than for AC fuses and AC switches. That should be really considered, that you have a certified equipment for that, as the fuses, the switches, and also the terminal boxes and the connectors and so on. When you connect the DC main cable, I'll come to this later, you see such a configuration. The PV combiner box must not be live, so you can switch it off. You have just usually a box there. Otherwise, there is a very high risk of an arc occurring as the entire power of the PV array can be present. Yeah, you don't need this combiner box or junction box with systems using inverters, with string inverters. So this makes it cheaper and less fault. There could be a lot less fault, also more shadow tolerant. And when connecting circuit breakers or circuit breaker devices, care needs to be taken to ensure the correct polarity, the energy flow direction. As I mentioned already, nowadays the plugs and the fail-safe, but not the circuit breakers and the other installation. You have to really check this before. Notes for module mounting. Sure, you should consider the manufacturer's assembly installation instructions. Also, if you use very thin framing or even frameless modules, you should really consider the recommendations of the manufacturer because there has to be a certain size of the mounting clamps and certain position of the mounting clamps at the modules. Otherwise, there's a danger that the modules will break under high snow load or high wind speed conditions. Yes, you should not drill additional holes in the module frame, so the warranty may be avoided. Installation should be carried out only in dry weather condition, also using dry tools. Usually, if you want to avoid the current of modules being carried, you do that at nighttime. Modules should be not stepped on during installation. This is more true than it has been some years ago because the cell thickness became less, and so the micro cracking of a cell, as the risk of a micro cracking is much higher than it has been some decades ago. Yes, sure, it's quite obvious you should not put heavy or sharp-edged objects close to them. Yes, the accessibility of flat roofs must be ensured after installing the modules for maintenance and inspection purposes. Skylights and roof access must be kept clear. Frameless modules are extreme risk of breakage during transport and installation and must be handled with great care. The corners and edges are particularly sensitive. I think that's clear. The most careful handling of the modules is ensured through vacuum glass lifters. 2 lifters or more are fastened to a clean modules in the area that's intended for the fixation. If you are in dusty areas, you have to make sure that the glass area is cleaned before, otherwise these vacuum glass lifters won't work. In large-scale systems or roof areas that are difficult to access, it can make sense to have a crane or supply or robots pre-assembled, pre-wired module assemblies. With many thin film modules and modules with string ribbon cells, the negative poles must be earthened. Just consider then the instructions by the manufacturer. Also with sun power modules, is N-type modules, the positive poles must be earthened. So here you see some pictures of some configuration. This is in China from a large power plant here. This is the DC connection box or junction box here, or combiner box. We open it here, so this is the inside here. So here all the different cables from the different string arrays come here. And instead of having here string diodes, there are protection fuses here. Here is a lightning protection. So if somewhere on the power plant is over voltage, it will be short circuit here to the ground. Here we have the DC switch. As I mentioned before, you have to switch it off before you do any installation because you have the full power, 127 kilowatt here online, and you want to avoid that getting electrical shock or some material will be destroyed. Here's the negative terminals arrive here. Sure, you don't need any. They are just combined here with a common ground. And this is the output. In the exercise, you will also design the output cable here. What is the best size of such an output cable from the power plant to the inverter? This is a calculation here. Just you have the resistance of the cable consisting here of the length of the cable here. Consider both lengths, plus part, the positive part, and the negative part. Then you have the cross section of the conductor cable. For example, 4 millimeter square or 6 millimeter square are typical values. And that's the electrical conductivity of your cable. Depends whether usually you have copper cable, but in some low-cost installation you have aluminum cable, so the conductivity is a bit less than the copper cable. For copper it's 56 meters by ohms by square millimeters. So you see, if we put that value in, so square millimeters will be eliminated here. So you have ohms here in the lower part, and while it's already in the lower part, we'll come to the other part. So you have ohms here. Meter will be eliminated by this length, and at the end you have an ohmic value here. We may also calculate the relative cable losses here. So you have the voltage loss along the cable times the current going through that, divided by the total power. So you have here the voltage of the PV power plant and the current at the PV power plant. Usually that's under maximum power point conditions. Here, if you go to the other part here, you have here the current going through the cable and the resistance of the cable that you calculated here. At the end, you arrive at that formula. So you have here, if you say, okay, we permit, for example, 3% of losses. So you put 0.03 inside here. You have the electric conductivity, the voltage, here the length of your cables, and the current going through them, for example, at the maximum power point. So we stop now talking about modules. We go to the next components that are inverters. Usually you have a grid connection there because grid is not working on DC, it's usually working on AC. So you have to adapt your DC power to the AC power. If you don't have an autonomous system, you have to adapt the frequency and the phase and the voltage of your generated power to the grid system. Here you see that the key functions there, first it converts DC to AC from the PV panels. It also controls the PV system. That means if you see next point also, it maximizes the energy harvest from the panel. So that's the maximum power point tracking. Sometimes we have large systems. The system operator says you have to shut down your system. That means power is reduced or even this whole system is shut off. This is also done in the inverter or by the inverter. It also manages grid stabilization through monitoring and communication. Can, for example, do a frequency or phase shift of your system and help even the system grid operator to get the system more stable. And this is critical, yes, to the integration of solar grid in the future, especially if you think about 100% of renewables, while photovoltaic gets always cheaper, wind not so much. So we'll see a large participation of solar in the future energy grid. Yes, you have technology, power is distinct, application needs, and so on. It's important, yes, to mention perhaps country-specific grid and safety codes. Fortunately, that's the case, so we have always to adapt. Usually the manufacturer do it via software update to put the inverter to the according of country codes. To give you an example, for example, there, if you have a large-scale power plant, you have to do a thing called fault riding through. That means if there's a fault in the system, you are not allowed to switch it off. You have to keep it for some time in order to avoid system instability. This is different in different countries. Usually in Germany we have 150 milliseconds. So for 150 milliseconds you have to keep the power on the system. Italy, for example, I think it's longer. It's almost half a second and so on. This should be homogenized. It's already on the way in the European Union. So we have a homogenized system there. So here you see the configurations of the inverters and the transformers. Usually if the power comes out of the inverters, even if 1000 volts, usually you have large scale systems. You feed into the mid voltage system, which is 20 kilovolts in Germany, and you have to have a transformer for that. Here's the MV mid voltage switchgear here, which also switches off and on the connection to the grid. For residential and commercial system, you may even have electrical vehicle charger and so on, and energy storage there. We come to this a bit later in some lectures. This is a basic configuration of an inverter with the integrated maximum power point tracker. So you have modules ranging from 1 modules to 25 modules. Then you usually have reached the 1000 volts of maximum permitted voltage. And then you have the inverter which converges here, for example, a single phase system in 230 volts single phase. And then you have a measuring device and a meter to see how much energy you have been generated. So you can either, if you have a feed-in legislation or power purchase agreement, this is sealed and calibrated, and you get money for the injected kilowatt hours. Yeah, very simple inverter, 4-pulse inverter. So you have here 4 switches here, for example, thyristors or triacs or GTOs or IGBTs or even MOSFETs, controlled here by the gate. And this control is made in such a way you just have either that or that in conducting operation, otherwise you would create a short circuit. If you put this here, then you would have positive voltage here on that part of the circuit. So you put this on a negative part, so ignite this and that. You can create pulses by that. For example, here, this is your reference voltage. You want to create such a sinoid. We are not able really to make a sinoid at the first place. You do it by smoothing the pulses later. Actually, you can do this, but this would create very high losses. Usually use pulses that are fixed current or fixed voltage here, and then you have a very short period. You have the full current, and if it's smoothened, you arrive in the medium at that current. The current is rising. The length of the pulse is increased here, and here at the maximum current, you have almost a full duration of your pulse width here. And then the pulse width is reduced, and then you do reverse pulses. So you switch off that switch here and ignite that switch. So this part of the circuit is then negative biased, and here this gets then to the positive part here. You ignite that one and switch off that one. And then you can here create negative pulses here and do the same as you did before here. Then you have this pulse pattern here. You do some smoothing, that's done here by some inductivity and capacity here. And here you have a transformer, depending on the voltage what you apply here, you feed into the grid. While this transformer is quite costly, during the last year it was substituted, so they work directly with connection to the grid, so-called transformer-less configurations, or they create high frequency here, and then you can, instead of using a large heavy iron transformer, you can use a ferrite transformer, which are really small and less costly than a big transformer. But then you have to transform that high frequency AC into DC again, and then it's transformed later at the right voltage into the 50 Hertz grid compatible frequency and synchronized to the grid. Depends, sure, in Europe and Asia it's 50 Hertz, Africa too. Only the Americas, they have 60 Hertz. The north part of Japan also 60 Hertz. This is now for 3-phase system. So you have, instead of 4 switches, you have 6 switches, and 2 switches are responsible for 1 phase here. It's done the same way as I explained before, but for each phase separately, and they are delayed. They have a phase angle of 120 degrees to each other. So you have a 3-phase system. This I was been mentioning already. So this is a high frequency step. So you just create a high frequency here. Then you can use a very small transformer here. Then you convert it into DC again, and then you use it converted directly to the grid compatible 50 Hertz. It's the same voltage, so you don't have to consider additional transformer here. So this is basically just to give you the right voltage here, and then here you create the AC here. This is the European efficiency of an inverter. This is quite a bad inverter to admit. So you have here at the relative load of 100% of the inverter, you have a quite good efficiency. But if you go to partial load, that's often the case because irradiance is not always close to the standard test conditions at 1000 watt per square meter. Usually we have only irradiance level of 200, 300 watt per square meter. So you're operating more in this range. In order to consider that, there was standardization of the so-called European efficiency in euro, and it takes into consideration not only the nominal power but also partial power. We take a look at that. So here we see the occurrence of irradiance levels. So you have here the statistics. First, this is also quite interesting to see the share of energy. If you take hourly values, you have those ones here. So they seem to be quite a lot at even high irradiance levels. It's on a 30 degrees inclined surface. I showed you also another statistics which was for horizontal irradiance level there, while in winter the sun is very flat and the frequency of low irradiance levels have been increased in winter, and therefore you see an increase in statistics there on this other graph I showed you at the irradiance chapter. The main interesting thing is here that you have minute values here. So you see that at minute values you have just a much higher share in high irradiance classes. This has to be also considered for the design of the inverters. So if you are able to do quick maximum power point tracking, you're able to profit from this high irradiance levels here also. If tracking is slowly, we observed that there are maximum power point trackers that took 20 minutes to get to the real maximum power point. So this is not suitable to profit from this minute values of the share of energy here. This is now the formula of the standardized European efficiency. So there are different weights. To see here, most of the weight is here at 50% of the nominal power. So if you go back to this picture here it's about 50%. So this is taken into consideration the most. This has a weight of 0.48 or 48%. 100% is only considered the nominal power output or the nominal efficiency of the inverter at 100% as only considered by 0.2. At 30% with a weight of 0.1 and so on, at 20% 0.13, at 10%, so very partial load here, 6% only, and 3% for 5% of the nominal power output. Graph showing that here. So this is a more modern inverter, so the curve is more flat, so it's even able to operate with high conversion efficiency at partial load, as you see here. And here you see the different weights in the formula here of the standardization. So this is most of the weight here, 48%. This is European efficiency. There's also very often used the so-called CEC efficiency. That's the efficiency according to the California Energy Commission, and it puts a higher weight here at 75% of the nominal output of the inverter. We come to that a little bit later. And it's quite interesting if you see, for example, at the first side, if you have just 100%, the nominal efficiency at 100% of the inverter, inverter 1 seems to be much better than inverter 2, but in truth is that inverter 2 has a better partial load capability and therefore should be preferred, while a lot of the irradiance values not only occur in the full load conditions, but most of them in partial load. The fact that full irradiance occurs very seldomly can lead to some quite interesting design recommendations. For example, usually you would say, okay, I have a PV generator of 1 megawatt, and according to that, theoretically, the output power could be 1 megawatt. I have to buy an inverter with 1 megawatt. It works mostly under partial condition then, that inverter, but you can save some money if you reduce the nominal power of your inverter. For example, if you buy 800 kilowatt inverter only, so this position, so you will lose some power. It occurs seldomly, but sometimes occurs that you have very high irradiance levels. Also, you have to consider the performance ratio because you lose according to the high irradiance level. You will also have a high operating temperature, and this will reduce your actual output. So the actual loss is very little. If you make the inverter 20% smaller from 1 megawatt to 800 kilowatt, but you only use 0.7% of the energy yield by that. So it's quite interesting. So you save probably about 20% of the inverter costs and you only lose 0.7% of the energy yield. This is true for Germany only. If you have some other locations, this might not be true. Then usually irradiance is higher. Then also the loss according to the reduction of the inverter size might be higher. You see here, you can even go down here to 7. Okay, then you have already 3.3% of losses. This might be considerable. But this helps you just in saving costs if you consider such effects. Here we have another concept. This is called the master-slave concept. It's not so applied nowadays anymore, but a decade ago it was quite common. So you have a master inverter with a power which is much less than the nominal power output of the PV generator. For example, you have a 1 megawatt generator and you only have a 300 kilowatt inverter. So a lot of time you operate that inverter, and that's important, very close to its nominal power output to 100% load, and therefore at a very high efficiency. If the irradiance is increasing and power output is increasing, for example, to 500 kilowatt, then you apply a second inverter, slave 1 for example, which is another 300 kilowatt, and together now you are able to digest 600 kilowatt. And so on, and you take the third inverter also with 300 megawatt, then only if very high irradiance occurs, and together then you have an inverter output of 900 kilowatt. While the inverters got better with time, so as you saw here for example, so this is good for master-slave configuration, so inverter 1 would always operate here in the high efficiency area. But nowadays inverter will look more like that one, so you have also quite good efficiency at partial load. So this concept gets a bit abandoned during the last years. Here you see the graphic representation of the master-slave concept. So if you have a single central inverter only here, you will have here a curve like this. And if you have 3 different inverters here, they operate always at a very high efficiency, especially here if you go to 10%, then your single inverter would work only at, how much is it, 89% of conversion efficiency, while here your master-slave concept would work in 94.5% of conversion efficiency. Another configuration that you have a single inverter for each string, so-called string inverter. So you connect all your modules in one string together, and then you have the DC switch. I've been showing you that before. So you can deactivate your PV generator from that, because if you want to do an installation here, they are open contact, they are not safe contacts as from the modules, and also the wiring of the inverter and so on, and you want to avoid that there's power there, especially while it's quite a very high voltage to the string connections. So while it's a power plant, also the power what comes out would be really high, so you have to have really that DC breaker. If you have 3 system, you can either put 3 different sub-generator or have 1 big generator and a 3-phase inverter. But you can also do this, you have to synchronize them, so you have here a phase difference of 120 degrees to each of those. It also should be mentioned that in order to balance the load of the different phases, you should not put all on one phase, but to switch the phases of the different sub-generators in order to balance the phases a little bit. This is quite interesting concept that you separate the maximum power point tracker from the actual inverter here. So you have a DC-DC converter and the maximum power point tracker at each module or each subarray. And this can help you, for example, if you have a big roof and you use different sides of the roof, and one roof, for example, is orientated towards east and one part is orientated towards south and the other part is orientated towards west. If you would put all of them together, it would act like shading there, and they would block each other out if they put all in one series conditions. So you separate them by using a maximum power point tracker for each subarray separately. So one for the east configuration, one for south and one for west. And then you lift it to the same, by this DC-DC converter here, you lift it to the same DC voltage, and then it's converted centrally in a central inverter here that feeds the energy being generated to the grid. Or more radical concept are the so-called module inverters or microinverters. There we apply an inverter for each single module. So each module and its inverter is a separate power plant. That means we have a lot of resilience here, and you can, even if one module is shadowed, for example by leaves or so, it doesn't affect the performance of the remaining power plant. Also, it's easier to install because you don't have large lines to be interconnected, and also it requires less planning because the layout of each sub plant is the same, because it just consists of one module and a single power plant. I come to this a bit later, discussing all the advantages and some disadvantages of that concept. Well, this concept is rather interesting. We have been investigating more in that. We compared different concepts and brands of microinverters and carried out some tests. The first test was the conversion efficiencies versus the input power, because you have to consider that we have different irradiance levels, so the partial load performance is really important. You see the performance of the different brands, what we found out. Here the SMA inverter was, for example, really good, even in partial load. Unfortunately, that particular inverter is not manufactured anymore because the production price was obviously too high and it couldn't compete on the market. Then we compared the weighted efficiency. As you already know, we just been discussing about the standardized European efficiency, which puts quite a lot of weight in low and medium irradiance level, and also the California Energy Commission efficiency, which put more weight on high irradiance levels. So here again, the formula here with the maximum weight on the 50% performance. This is a ranking of the different manufacturers. So here SMA was the best with the European efficiency of 95.41%. So this is relative to the best is 100% because it's the best, so it's 100%. End phase is only a little bit worse. So you see here it's only a difference of 0.2% towards the best, with a European efficiency of 95.22%. And even the worst here, the European efficiency is about 90%, and in relation to the best, the difference is about 5.5%. Let's compare it to the California Energy Commission efficiency. What you see here, so you see here that the weight is more on the 75% of nominal load, which doesn't occur here at all, but here is the highest weight on that. And let's see whether something changed. Yes, something changed. The end-phase inverter performed the best here. So it's designed obviously for the CSC efficiency with an efficiency of 95.55%, power 1, and so on. SMA is only on the 4th place, but you see the difference here is about only 0.5%. So this is very close together. But you see here some inverters performed not so well, but we'll come to this a bit later, especially if we take a look at the energy yield. We installed all the modules on the roof of the university, and then we compared them according to the injected electricity into the grid. This test also takes into consideration the dynamic capability of the microinverters. So the MPP tracking capability is also checked by that. As you see on this graph here, you see some of the inverters. We have quick changing irradiance. Some are not able to react to recover if you have an increase of irradiance, and contrarily, they are performing worse than it been for the irradiance level before. You see the two extremes here at quickly changing irradiance. So some are really able to cope with the changing irradiance, some are not. And this led to the following ranking. So we had here the winner is ABB inverter, which showed the maximum yield during a year. Second place SMA. You see the difference is quite high, especially if you go to the lower performing devices here, that the difference in energy yield, and usually if you get paid for each kilowatt hour being injected, this is a considerable loss of about 22% or even 24.4% compared to the best ones. So this is really even more interesting than just the pure efficiency and the European weighted efficiency performance as you saw here. So this gives this yield value is for the end consumer, I think, the most important value. So the comparison between microinverters and string inverter. So the microinverter are able to maintain a robust and constant flow of power even with shade on one of a module panel or more of the panels. They serve an individual module only, so the power performance and the overall health of each module can be tracked and monitored in real time. If there is a single module in a string that is malfunctioning, the installer would need to go on the roof and find the single module that is affecting the string and the total power output. This is even more true if you have a large-scale central power plant with thousands of modules and you don't have specific monitoring devices for each module or even each string, and so you have to check the whole power plant in order to find the malfunctioning module. Different modules are in a string have different maximum power points. This was the other concept you saw before with the solar edge concept, where you have a maximum power point tracking device on each subarray. And this is even more true here because you have a maximum power point at each single module. Additional advantages is more easy logistic to spare parts, while if you have central inverters for each power level, you have to have a separate inverter, and also for the different voltage levels and so on. And here you have just one single type of inverter here. And this is also for the installer. If sometimes the client orders a lot of big power plant, and if he later decides he wants only half of it, you can keep the half without redesigning and so on, and without changing parts, because you can keep the spare parts still for other projects. Price should go down. It went down already a little bit, but not as much as is expected compared to modules. Although the decrease rate is not very high, but theoretically there's a potential for cost reduction due to mass production. It's also this gradation effect that occurs less if you have a lower DC voltage applied on your module. This is called PID, potential induced degradation. I will discuss it later when we come to the defects. An additional aspect is the grid support. While if you have a large variety of different orientation of PV modules, they reduce the typical overproduction during midday, because nowadays most modules are strictly orientated south. So you have a lot of power production in midday, but less in the morning where you need it, and less in the evening where you need it also. If you can distribute it more towards different orientations, then the output power of PV power production in a country, for example, is more balanced. Also, if you would install in a steeper angle, a PV generator during winter would even increase. Usually we have a lack of power there. These are some examples of those power optimizers. That it's not really a microinverter. You have just a maximum power point tracking device at each module or at each subarray, as we saw before. So the system layout for grid connection. So this is the concept what you have in 1.5 million German households. They have a roof, they have a PV panel there, they have then a DC junction box here where you interconnect all these modules, usually in series, or some series you can do directly. You don't need a junction box for that, but sometimes you have several strings and you have to connect these strings in parallel, which is then there. And then you have here the inverter. Here you see the injection meter and the consumption meter. These are separate. In some countries this is one device only, which you just get compensated the balance between the injected electricity and the consumed electricity. In Germany you have different tariffs for the consumption tariff and the injection tariff. Formerly the injection tariff has been very high. For example, in the year 2000 you get paid about 56 cents per kilowatt hour of injected PV electricity, and you paid only about 22 cents per kilowatt hour. Nowadays you pay 30 cents per kilowatt hour for your consumed electricity, but you only get paid about 10 cents per kilowatt hour for the injected electricity. Then you have the grid connection and the local loads, which gets more important. While if you are able to generate your own electricity for 10 cents per kilowatt hour, you should rather consume it on your own rather than buying it from the utility for about 30 cents per kilowatt hour. Here is the system layout. You have the PV generator, here consisting of 40 modules. 10 modules each are interconnected in series, the rest is interconnected in parallel. And then you find here the interconnected strings, usually via string diodes or here with fuses. Then in green you have an over voltage protection device that short circuits here the power plant in case of over voltage here. Then you have a wiring to the main switch, or it's integrated as we saw before, and then you have some wiring to the inverter, and then you go via the meter to the grid. For system sizes above 30 kilowatt systems in many countries, there is an external switch required, so you can switch it off via utility, or there's a kind of remote control for fire brigades and so on, so you can switch it off from far away from the power plant. For large system configuration, the utility has even more control over the system. For example, here you have a medium voltage grid injection here. So you can do static grid support, that you have the reactive power being controlled. You can adjust the cosinus phi, whether it goes to inductive or capacitive. Also can do effective performance limitations, for example, due to overproduction, and you can adjust the inverter accordingly. You can also do dynamic grid support. For example, it's been blind power feeder, but it's reactive power, I think is more common word for this. And as I already mentioned, the fault right through effect. So some countries that is required that you, even if there is a problem there in the grid system, you have to not switch off, but continue your power production. So on network security management, also possible that you do a power limitation, 60, 30 or 0% of the, or 100% of the power output will be limited. Some pictures here, you see a 20 kilovolt mid-voltage grid injection. Here you see a transformer. I told you usually the inverters have an output of maximum 1000 volts, but if you want to go up to 20 kilovolt, you should have a transformer here to adapt the voltage to the mid voltage here, to the medium voltage. Here's a high voltage, same, but only at higher voltage, 110 kilovolt, at a Chinese 100 megawatt system. So the requirements for grid connection, this is the German legislation for that. So for system sizes below 3.68 kVAr or kilowatt, the reactive power should remain in this range, plus minus 0.95 cosinus phi. Then remote control power limitation or disconnection or restriction to the maximum active power of to 70%. If you go to higher system sizes, then the restriction get more, so you have more protection and so on. And if you go, for example, more than 100 megawatts, you have a lot of restrictions. The utility can control your system. For DUSI's monitoring, there are some devices. You can even have an app on your smartphone and check your system while you're at work and so on, and also some visualization and even alarm for failure. So they send you a short text messages if there is a problem. For example, if you install an Irradiance sensor, but the system is not performing as expected, they send you a message on that, and you can send someone to the power plant to check what's wrong. So we come now to the exercise. First part is like before, we have the same irradiance profile and the temperature profile, but now we see the adaptation of the optimal resistance, so we stay in the maximum power point. This asks, so you do for the different cases, you should calculate the different value of the resistor. Next part is for DC wiring. So you should take into consideration first what's the maximum number of modules and the according power output. string module in series connection to make sure that voltage stays under 1000 volts. That's especially important for cold temperature. Imagine you have a very cold winter morning, sun comes up. Even if the irradiance is quite weak, but the voltage is already there, and if you have minus 20 degrees, for example, this is kind of worst case conditions, the voltage is highest. And if the voltage is higher than 1000 volts, for example, your inverter may be destroyed, or other components may be not working correctly anymore, or even it could be an insurance problem, so because you are not able to make sure that the voltage always stays below 1000 volts, because if you have higher voltages than 1000 volts, then the standards are changing. These are model data. And then is another question here, what is a minimum diameter for a Cooper cable of from a string of PV modules to the DC connection box if the maximum permitted cable loss is 0.5%? What would be the gain in electrical energy for a 1 megawatt power plant during its lifetime? Nowadays it's even longer, not 20 years. People even are calculating with 25 or even 30 years, but this is a very conservative estimate. And if you, instead of 1000 volts, if you would change the system voltage to 1500 volts or even to 2000 volts, sure, you have to consider higher insulation costs, but you can consider less Cooper losses or even less Cooper for your wiring and so on. So this should be calculated. Here's the financial advantage. What would this bring if you consider the higher costs for the cable, for the insulation of the cable, but less cost for the Cooper and so on? This is a configuration. So you have here a PV generator with N modules in the series connection. The size of the modules, because you have to calculate the length of the cable, should be 2 by 1 meter, and you put it on this together on the small side. So you have a 2 meter, 1 meter, 1 meter, 1 meter. So if you have, for example, 40 modules, this is 40 meters and so on. And so you have 40 times 1 meter. And here the distance to the DC connection box should be 5 meters and 5 meters. And so you can calculate these losses here and so on. We do it in detail for the exercise lecture, and you can calculate it. This is what already from the formula I've been giving you. You calculate the losses. So this was, yes, it's a repetition of that foil there. So you just do the calculation here, also for the worst case conditions. Remember here, consider the temperature coefficient. I blanked this out so you don't see this solution already. This will come when you did it alone on your home, so you learn more rather than I just present the results for you. So this is again just more in details about it. It's actual cable losses. So you just first calculate the length of the cable required, calculate the cable losses at 1000 volts. The losses, there are two extremes what you should consider. Maybe that was not visible by the task what you see here. So because the current is rather different, so we take into consideration two extremes. So we just take the highest current occurs here if you have standard test conditions, 1000 watt per square meter, and it occurs for 1176 hours per year, and you don't have any low irradiance there. That's one extreme case. So that's dark or either full irradiance, or the opposite, we have an equal irradiance, not over 24 hours, that would be exaggerated, but during 12 hours. And so you have an average irradiance during that period of time, so about 268.6 watt per square meter, so only a fourth of that irradiance, and accordingly only a fourth of that current. And calculate for both cases then. So the number of strings to build in parallel, cables required, and so on, and then you calculate the same thing for 1500 volts and for 2000 volts, the actual losses and the losses during 20 years, and this will be then calculated in terms of money. Here you just have again the values here. Processed Cooper price is 10 euro per kilogram, so you should know how much Cooper your cable needs according to the length and the diameter. And the gain is here, you get 8 cents per kilowatt hour, so it's quite a common value what you get here for your PV electricity. Then you do the cost calculation, so just the total cost of your cable is the insulation costs plus the Cooper costs. Calculate the volume and the costs and so on, and the full specific costs, and then You calculate for the different voltage levels, for the different irradiance or full irradiance for a short time or equal irradiance during 12 hours each day. Then you do the financial side and calculate all that, and then you should present the saving, if there are any. Maybe it's even more expensive, there are no saving at all. So they have the reduced cable costs and or less losses, and you have to do it for every voltage separately and or for each case separately to full irradiance because the maximum current is highest, and for the second case also if you have an equal irradiance. You also same for 2000 volts. And then you should result, should you do this measure, does it make sense to increase the voltage, or how much would you gain, or how much would it cost you? That's it for today. Good luck with the exercise, and we see us on Monday with the results of the exercise. Thanks a lot.